Hello everyone. For those who don't know me, I'm Vinay and I'll be doing a quick demo of real-time face recognition. You must be wondering why I didn't do a video on a technical paper. The simple reason is that I wanted to share what I've learned from this course. As part of my curriculum, I had to do a project on building automation system. The first thing that came into my mind was real-time face recognition for authentication of family members in the house. This sophisticated security approach eliminates the use of trivial biometric systems. You must have seen in many Bond and Mission Impossible movies where the spies can easily fool and breach the biometric security system. Without further ado, let's move on to the demonstration of real-time face recognition. The heart of this project is Raspberry Pi 2 and its interface with webcam. If you want to make it cost efficient, you can use Raspberry Pi Zero, which costs $5 and a cheap webcam. Now I'll be discussing the algorithm of face recognition. The first and foremost thing that I did was to create a database which will have several images of family members. And then I'm going to train those images using LBPH and SVM. Let's discuss about how to perform texture matching using local binary patterns. Local binary patterns is an important feature descriptor that is used in computer vision for texture matching. It was first released in 1990 and subsequently various modified versions have been released. Firstly, we convert the input color image to grayscale since LBP works on grayscale images. For each pixel in grayscale image, a neighborhood is selected around the current pixel and then we calculate the LBP value for pixel using the neighborhood. After calculating LBP value of the current pixel, we update the corresponding pixel location in LBP mask. It is of the same height and width as the input image, with the LBP value calculated as shown in the figure. In the image, we have 8 neighboring pixels. But how is LBP values created? To calculate the LBP value for a pixel in grayscale image, we compare the central pixel value with neighboring pixel values. We can start from any neighboring pixel and then we can traverse either in clockwise or anti-clockwise direction, but we must use the same order for all the pixels. Since there are 8 neighboring pixels, for each pixel we'll perform 8 comparisons. The results of comparisons are stored in 8-bit binary array. If the current pixel value is greater or equal to the neighboring pixel value, the corresponding bit in the binary array is set to 1. Else, if the current pixel value is less than the neighboring pixel value, the corresponding bit binary array is set to 0. When we consider classification and machine learning methods, SVM is one of the simple and easy to use classification method. Regarding image processing, there are a number of uses of SVM. Image classification and handwritten character recognition are some uses of SVM. SVM can be easily used to classify feature vectors extracted from images. SVM is supervised learning method. It defines separating hyperplanes between labeled datasets. These hyperplanes can be used to categorize new dataset for which we don't know the class label. To understand the problem easily, instead of hyperplanes and vectors in high-dimensional space, I use lines and points in Cartesian plane as shown in the figure. Here the problem is to select one from all possible lines which can be used to separate two classes. After defining such hyperplane, we can categorize new sample data to a class using that separating hyperplane, but it is difficult to define an optimal hyperplane. Based on a criterion, we can estimate the best line which separates the two data sets. The operation of the SVM algorithm is based on finding the hyperplane that gives the optimal separating hyperplane, that is, the largest maximum distance to the training examples. Support vectors are the elements of training set that would change the position of the dividing hyperplane if removed. Support vectors are the critical elements of the training set. Object detection using Hall feature-based cascade classifiers is an effective object detection method proposed by Viola and Jones in their paper, Rapid Object Detection Using Boosted Cascade of Simple Features in 2001. It is a machine learning based approach where a cascade function is trained from a lot of positive and negative images. It is then used to detect objects in other images. Here we will work with face detection. Initially, the algorithm needs a lot of positive images, images of the faces, and negative images, images without the faces, to train the classifier. Then we need to extract features from it. For this, how features shown in the image are used. They are just like a convolutional kernel. Each feature is a single valued obtained by subtracting sum of pixels under white rectangle from the sum of pixels under black rectangle. Now all possible sizes and locations of each kernel is used to calculate plenty of features. Just imagine how much computation is required. Even a 24 by 24 window results over 1,60,000 features. For each feature calculation, we need to find sum of pixels under white and black rectangles. To avoid this, they introduce the integral images. It simplifies calculation of sum of images, no matter how large may be the number of pixels, but the operation involves just 4 pixels. But among all these features we calculated, most of them are irrelevant. For example, consider the image below. Top row shows two good features. The first feature selected seems to focus on the property that region of eyes is often darker than the region of nose and cheeks. The second feature selected relies on the property that the eyes are darker than the bridge of the nose. But the same windows applying on cheeks or any other place is irrelevant. So how do we select the best features out of 1,60,000 plus features? It is achieved by AdaBoost. For this, we need to apply each feature on the training images. For each feature, it finds the best threshold which will classify the faces to positive and negative. But obviously, features with minimum error rate, which means they are features that best classifies the face and non-face images. The process is not as simple as this. Each image is given an equal weight in the beginning. After each classification, weights of misclassified images are increased. Then again same process is done. New error rates are calculated, also new weights are calculated. The process is continued until required accuracy or error rate is achieved in order to get the exact number of features to detect the face. Final classifier is a weighted sum of these weak classifiers. It is called weak because it alone can't classify the image, but together with other forms a strong classifier. The paper says even 200 features provide detection with 95% accuracy. Their final setup had around 6,000 features. Imagine a reduction from 1,60,000 plus features to 6,000 features. That's a big achievement. This is the demo of real-time face recognition. The code is written in Python. As soon as I run the code, the images in the database are going to get trained using LBP and SVM. The camera starts taking the video feed and each frame is checked by a Haar cascade whether any face is detected or not. If the face is detected, then the face is stored and compared with the database. If the deviation of the image is less than 25%, then the person is allowed to enter the home, thus adding a sophisticated security feature to the smart home. I hope you enjoyed the video. Thank you and have a nice day.